Okay, maybe I can start now. I think I will be talking something everybody knows about the importance of wind current in MI coupling. And also, I will talk about a model that combine the CRCM and RBE. And actually, I want to take this chance to thank Dick Wolf. You can't hear me? Okay. Yeah, I'd like to thank Dick Wolf for the collaboration we have 15, I don't know, I forgot, maybe 14 years ago. And I have the comprehensive wind current model established. At that time, it's kind of combined the Fock wind current model and the RCM. Okay, first I'd like to thank my collaborator Tom Moore, Alex Grosser, and Natasha Busukulua for this work. And here's the outline of my talk. And so, yeah, I think I don't need to say this. And first I will talk about the source of the wind current, one of the important sources from the ionosphere. And then talk about the role of the wind current in the MI coupling. I think this is, you have seen this many times in this week, so I don't have to repeat that. And as I said, recently I have combined two models, CRCM and RBE. This is comprehensive wind current model and the radiation belt environment model. The reason to combine is just because you have two models, and then you have update or upgrade for two models. It's just too troublesome. And actually, two models is very similar. The major framework is very similar. So to combine them just save time and more efficient. And also actually because in the past CRCM is mostly deal with the wind current and the ionosphere, and RBE is the radiation belt prediction model. And actually these two plasma population they couple to each other, so it's very natural way to combine them. And then I will talk about how SIMI will be used to support two missions, twins and Venn probe. This is some old work we have done with Tom, and we simulate actually we simulate how the wind current evolve during a LFM substorm. So first we want to build up the boundary condition for the wind current, and we release particle from the solar wind, from the ionosphere H plus and ionosphere O plus. Release them and using the test particle code and trace and see how they get access to the wind current. And we launch millions of ions, and from this the test particle simulation we can establish the 3D ion pressure and density. So for the solar wind particle, we found that they enter the wind current mainly from the dawn flank and then bypass the energization process in the plasma sheet. However, for the O plus, the ionosphere O plus, they enter the wind current mainly through the lobes and the plasma sheet. And then you will see this is the typical trajectory of the O plus, the release from the ionosphere, and the color of the trajectory is the energy. So you can see when they travel from the ionosphere and then land in the plasma sheet, and then eventually get trapped in the inner magnetosphere, and they get and at the same time they get energized. You can see that this is the energy versus the time of flight. And in the beginning, the energy is very low, like 10 eV, and then you can see a very sharp jump here, and at the near the plasma sheet. At this time, actually, the magnetosphere is collapsing. It's a substorm dipolarization. So the O plus get the anisotropic energization. You see the sharp jump in energy, and the energy reach to the wind current energy, like 10 keV when they get into the wind current region. Okay, this is the logic of the model of CRCM. Actually, it's the same as the RCM, and Dick already talked about it, but I got the formula. How we have from the wind current distribution or pressure gradient, how we calculate the fuel line current, and then how we solve the equation in the ionosphere to get the potential distribution. And for this potential, we map for the field line into the magnetosphere and use this convection to advance the particle distribution. And I steal the figure from Jerry Goldstein. So as I said, I combined the CLCM and RBE to form a comprehensive inner magnetosphere ionosphere model. I call it SIMI. So this is just another way to show the model logic. So this is all the input parameter to the model and the solar wind and geomagnetic indices. So with this input, we can, and also, oops, this is supposed to be some sigma. Okay, this is the conductivities, and with the polar cap potential drop, we solve the convection electric field, and then we have the input drive, the magnetic field model, and also we have a plasma sphere model. And with the plasma sphere model, we can model the wave diffusion, and also we have a plasma sheet model to give us the boundary condition of the wind current and radiation belt particles. So run the SIMI. And this is the main output of the SIMI model. It's energetic ion flux from 0.1 to 400 keV. And for an energetic electron, we have higher energy up to 4 MeV. And also, we also calculate the precipitating flux at the ionosphere. And see all this, the purple boxes are all the model output. So you can see SIMI got a lot of output. Ion flux in the magnetosphere, and also precipitating flux in the ionosphere, and also with output field line current and the Savarowi electric field, and also we also output the plasma sphere density. And this is the model equation. This is the three major equations we solve in the model. This is just the Boltzmann equation for the energetic particle. So we consider drift of the particles and the energy of the diffusion in the velocity space. And this mainly comes from wave-particle interaction. And for ion, we can also consider charge exchange. And also we have the loss cone loss. So this is the equation we solve to get the ionospheric potential and also field line current. No, sorry, ionospheric potential, sorry. And this is the equation we solve to get the plasma sphere energy electron content. Okay, this is all give you more detail about the input. So for the solar wind data, we're using ACE or wind data. And yeah, this is how we get the AE or DST from the Kyoto or from the US USGS give also have even more time, higher time resolution DST data. And for the magnetic field, we use both the empirical model of second angle and also we use the physics-based MHD model. Electric field, to get us the, if we use the Weimar model to give us the potential at the polar boundary, but if the semi coupled with MHD, we don't solve the ionospheric potential. We just MHD model will take care of that. And the partial sheet model, yeah, we have both the empirical model and also as I show, we have some test particle work in the past to give us the boundary condition of the wind current. And also, if the model coupled with the MHD will provide us the boundary distribution for the wind current and the radiation belt. So the wave power and diffusion coefficient, we use some Gaussian fit to the Kress and famous data, and the coefficient provided by J. Albert and also a scientist at Goddard, Chouhua Zheng. Here I'd like to show a simulation of the April 5th to 9th, 2010 storm, and we did 2 runs. And the first run, we considered the self-consistent and MI coupling electric field. And the second run, we just used the empirical Weimar model in the entire simulation domain. I just want to show the MI coupling is how important that will modify or control dynamics of the inner magnetosphere. And this is the 10 to 30 keVH plus the first run. This is the equatorial flux. This is the sun on the left. And then you can see with the self-consistent electric field, we see the peak of the ion is on the night side, more toward the dawn. The peak is more toward the dawn. But if we use the Weimar model, you see the peak of this ion is near pre-midnight, in the pre-midnight sector. And in this storm, we have very nice twins data, twins ENA data. And this is the twins from the ENA emission from twins 1 and from twins 2. And you see the low altitude emission here. And I hope you can see it. Yeah, this is the wind current emission, the ENA emission from the wind current here. And okay, we calculated ENA emission according as corresponding to the simulated ion flux, and this is the semi-calculated ENA, and then we compare with the twins data, and we got the local time distribution pretty consistent with the data. And if you use the Weimar model and get this ion flux and generate the ENA, you will see the local time distribution doesn't match the data well, and you can see the semi model had a better agreement with the twins data. And we also compare with the Akebono data to look at the radiation belt, how semi can predict the enhancement during the radiation belt during the storm. And this is the Akebono data with energy larger than 2.5 MeV. This is the L time plot. And okay, Dan is here, so finally you have seen some work on radiation belt. Okay, this is the DST, if you can see the DST overlay on this plot. And this is the semi-run with the self-consistent field and with the wave diffusion with Whistler Chorus. And you can see also we produce the enhancement of the radiation belt electron in the recovery phase here. And this is the run with the Weimar, and same run, but just use the empirical model, you also see the enhancement during the recovery phase, and actually, yeah, they look similar. But if you look more carefully, you will see the enhancement from the self-consistent electric field. We get the higher or the stronger enhancement during the recovery phase, and we wonder what caused this enhancement. So we do another run using the same as the run one, but we just say, oh, okay, it's the no wave diffusion. So without wave diffusion or wave energization, you don't see much enhancement during the recovery phase. So we confirm that the enhancement you see here is due to wave-particle interaction. But the question is why we use the self-consistent field, we got stronger enhancement. So we look at the lower energy electron. So this is the wind current electron is in hundreds of keV. Is at during the peak, near the peak of the storm. This is from the run with Weimar model, and the same thing. This is the wind current electron near the peak of the storm, and using the self-consistent field. So you can see the difference between these two plots. With the self-consistent, we got stronger wind current electron, and this will provide a strong seed population for the wave diffusion, wave energization. And that's why we got stronger enhancement for the radiation belt electron during the recovery phase. And as I said, we also calculate the electron precipitation into the ionosphere. So this shows the two run, and this is the ionosphere. Sun is on the left, and you can see what I'm showing here is the energy flux. So you can see in the first run with the MI coupling considered, you see stronger precipitation around dawn, and the one with Weimar model, the strong precipitation is in the pre-dawn sector, and also the energy flux is lower. And with this energy flux, and also we know the mean energy for the precipitation, we can estimate the conductance in the ionosphere. So of course, you see stronger precipitation give you stronger conductance. So this is something we want to do in the future. We want to feedback from the precipitation. We calculate the conductance and feed it back to the model and modify, and then that will modify the convection field. This is something we plan to do. And actually, this, I think, Rice convection model have been doing this for a long time already. Okay, now I'd like to talk about also the model, how the model will help to interpret some feature we saw in the Venerian flow. I like to look at the dropout event from the storm November 14, 2012. And this is the data from RB space. And this is the energy time spectrogram. And then you see near the parity or the apogee of the spacecraft, you see some dropout here. And here is the spacecraft pretty close to the Earth, so we don't understand why there's some flux dropouts. The spacecraft should be in the wind current or radiation belt region. So we did two run. Alex did two run. The one is we use the semi-Bessel-Russ two-way coupling, and we two run. One is the initial condition is like no wind current, it's a very weak wind current. Just use the initial condition from the MHD model. In the second run, we have a better initial condition using the quiet time wind current model from Shelton et al. So the first run, with the initial condition without ring current, we see no dropout. And then the one with ring current, then we see that we can reproduce the dropout seen from the outspeed space data. So we see how or why the two run give us different results. So this is the first run. We see the dot here is the spacecraft location, and the color here is the field line current. And then you can see the region 1 and region 2 and region 1 current. And for the first run, you see the spacecraft is is inside the region 2 region. And for the second run, the RBSP-A is in between the region 2 and region 1 current, where the field line will change, very sensitive to where you are. We will change rapidly from very dipolarized field to very stressed field. So we believe, okay, so so even the spacecraft doesn't change much in this between these two times, but the spacecraft will connect to the field lines very dipole-like and also or very stressed. So that's why you see the dropouts or the spacecraft is in and out the close line region or and very stressed field line region. So that's why you see the flux high and low. So when the field line is and the spacecraft connect to the field line very stressed, where there's no not much ring current there. Okay, finally I'd like to talk about how CIMI will support the mission, and we are working on real-time run of the CIMI, and then we produce the flux along the RBSP A and B orbit. At CCMC, we're working on this. So here show you some example. I downloaded this 2 days ago, so you see the February 10th, but if you go, but you can go. I can't tell you the website, but anyway, now it's running real time. So we still have some problems. You can see some gaps. Sometimes the code doesn't work. But anyway, we are working on it. But I want to say is, and here is the energy time spectrogram along RBSP A here, and this is the electron flux, proton flux. This is along RBSP B. So we want to run that in real time and provide what the RBSP will see. And if the reason is if you see something interesting in the data, hopefully you look at the run, and if you see the similarity, you can see provide the reason why you see that's interesting feature. And also, actually, the run can do the CIMI can plot many things that the RBSP won't see. So we have the global flux distribution. So yeah, this is the electron in 15 keV, and this is the low energy ring current ion. So we can also will provide that on the website, so you can see how CIMI predict the global distribution of the ion. And also our plan will put more physical parameter like electric field or atmospheric density. This all output from CIMI. And yeah, this is still a work in progress. So once we have confidence the code is running good, running fine, then we will put that in the public site so everybody can see it. And another thing is for twins. Okay, fine. Okay, one thing Jerry talked very nice about twins, but the twins team published a lot of paper. But the problem is we found not many people outside the team use the twins data. So we want to address this problem. So our plan is we want to identify storm with good twins data. Okay, like this, we are And then we have Joe Perez at Auburn to do the twins, the inversion, the image inversion to get out the ion flux. We call it twins ion. And also, we will run the SIMI and give you the simulated ion flux. So with just like one-stop shopping, you get the ENA image data, and you have the twins ion data, and also the SIMI ion. So we're also working on this. So once this is done, we will put in the twins website. So hopefully, come to visit the site, and then if you find something when you are interested, you can look at whether twins give you the some hints of what's going on, because the twins give you the global picture of the wind current.
Thank you very much.